Jim, come on up. Jim Rea is a software developer with 35 years of experience. He developed the ProView Products Overview, which was the 7th program on the Mac platform back in 1984, and Panorama, both of which are database products. And Jim is here to talk today with us about database design and his insights into that topic. So please extend a warm welcome. Jim Rea.
I won't be able to read that. Oh. Can you read that? How do I advance then? Okay. Which goes forward and back. Okay. Okay. And you also have a way to click. Okay. Okay. Hello. So, is this a little loud? Data organization is one of the first applications that drove the early computer industry. From those early days, database storage has been synonymous with data storage on disk. In the past decade, however, in-memory databases are a fast-growing segment in this market, so I'm going to talk to you about why that is and how that works. As you probably know, historically, database programs have been disk-based, as I just said. In other words, the data is manipulated directly on the disk, on a hard disk or SSD, and only tiny bits of data are brought into memory at a time. An in-memory database program, on the other hand, loads entire databases into RAM memory and works with it there. As we'll quantify in a minute, RAM memory is much, much, much faster than disks or SSD drives. So this speed difference can not only allow databases to operate the same way faster, but it can also enable completely different strategies for database manipulation and opens up new opportunities. So that's what I'm going to be talking about during this talk. Because of the advantages of in-memory database technology, it's now being used by some of the largest players in the market, as well as many newcomers that have come up to take advantage of this. Now, some observers think that in-memory database technology will eventually take over the majority of the database market, and I think that probably is the case. Hey, what the heck's going on there? Oh, that's my slide. I'm hoping that this talk will help you understand the advantages of this approach, and that you'll keep it in mind the next time you're planning a new database project. Now, if in-memory databases are so great, why haven't we been using them all along? After all, other types of applications are all memory-based. For example, spreadsheets, word processors, drawing programs, just about everything else, they all work by loading the data into memory and working with it there, and only use the disk for saving. So why have databases been different? Now, part of the answer has to do with the fact that databases can grow much larger than other types of documents. A very large database can contain millions of records, which is bigger than most letters or spreadsheets, that sort of thing. But for the rest of the answer, we have to travel back to the early days of computers when the first database applications were invented. We had bell bottoms, we had disco, and we had computers with really, really, really tiny amounts of RAM. So in 1970, there'd usually be only a few dozen kilobytes of memory. That's kilobytes with a K, not megabytes or gigabytes. So there's no way that you could fit a million records of data or any reasonable sized database in that small amount. So they had to figure out, how are we going to handle this data when we can't fit it into memory? So they had to put things on the disk. But disks are slow. At that time, the access times of hard drives were about 12,000 times slower than RAM. So how did they do that? They came up with an algorithm called B-tree indexing that was invented to improve database performance. And I'm going to talk quite a bit later about what the advantages and disadvantages are of using that technique. So let's jump forward to 50 years to today. Everything's much faster, bigger, cheaper, And we have a new technology, SSD, that wasn't even dreamed of in 1970. I'll talk more about SSDs in a minute. But first, I want to focus on the capacity of RAM, which is now in gigabytes instead of kilobytes. So these days, even the lowest end computer you can buy has 8 gigabytes of RAM. Now, is that going to be enough to hold our data? Good chance it is. In preparing for this talk, I looked for a large database that I could download from the web, and I found on the FAA website, I found this database. It contains 50 fields of information on every registered aircraft in the United States. So like how many wings does it have, how many engines, how many seats. That's almost 1/3 airplanes, helicopters, gliders, blimps, etc. So you might be surprised, that seems like a fair amount of data, right? But if you load it into RAM, it only takes 81 megabytes of memory. So if you have a typical computer with 8 gigabytes of memory, this database would only take 1% of that memory. At that rate, a million record database would take up only 3% of memory. So the point I'm trying to bring across is that these days, most applications, you can fit the data that you need to work with in memory, and there's no reason, there's no need to have to use the disk. Now, I'm sure many of you are wondering, though, if in-memory is really needed, since now we have SSD drives, and they're about 1,000 times faster than hard drives. So does RAM really help us that much more? And in fact, it's actually still 1,000 times faster than an SSD drive. Although, you might think, well, they're both electronic. They don't have any moving parts, right? But they're not the same, because SSDs are non-volatile. They keep the memory when you turn the power off. RAM, when you turn the power off, it's gone. So there's a whole bunch of electronic complexity that's needed in every cell of an SSD in order to allow that, and that's why it's 1,000 times slower than RAM. There is another issue with SSDs I just want to mention, which is that because of all this complexity of keeping it permanent, an individual SSD bit can only be modified about 1,000 times on average. So in order to get around that, because you probably want to do more than 1,000 writes to your SSD, they build them with extra capacity and load leveling hardware right in the drive, so that it sort of spreads around, and if you change a bit, it might actually move to another location so that you're not writing any one spot over and over and over again. So that's why you're able to use them for files and stuff like that. But this issue of how many times it can be modified can be a real issue for super high volume applications like airline ticketing or stock exchange trading. And this is one of the factors that's driving in-memory database adoption, especially at the high end. So if you're interested in all these details, I found this extremetech.com article that talks a lot about what I was just talking about the differences between RAM and SSD technology. Now, it turns out in practice, because of the way computer system architecture is organized, RAM is actually even faster than the previous slides I just showed you suggest. And this is for two reasons. First of all, RAM is directly connected to the CPU through a high-speed bus. It's right there. So the CPU has full access to all that raw speed that we were just talking about. A hard disk or SSD drive, however, is not connected directly to the CPU. Instead, it has to go through both hardware and software layers, and each of those layers add quite a bit of extra delay over that internal bus. Another source of delay is that the disk or SSD drives can only be accessed in entire blocks, which are usually 4 kilobytes or more. So even if you just want to modify a single byte, if it's on a drive, what you have to do is read the entire block in, modify what you want, and then you write it back out. So it's quite a bit more delay if you're just want to write things individually. So all of these factors add up to a performance difference of about 10,000 times or more. That's from SSD or RAM. And of course, if you were switching from a hard drive, it's even more of a difference. So there's a lot of motivation of, we can get a big performance improvement if we can switch to in-memory instead of working with our data on a disk. So let's turn our attention to how RAM can be harnessed in a real database application. So one quick and easy way that you might be able to do that is to create what's called a RAM disk. Some of you, those used to be common 20, 30 years ago. A RAM disk carves out part of the RAM and uses it as if it were a disk or SSD drive. And the advantage is that you get quite a bit of speed improvement without having to make any change in your software. So you can just keep using the same software. The software doesn't even know that you've changed anything, but the underlying performance is better. But there isn't any free lunch. First of all, using RAM this way is still a lot slower than using it directly because you still have the overhead of the operating system, and the data is going to be transferred in blocks instead of bytes because that's how the operating system does it, even though the RAM doesn't have that restriction. The operating system and the software you're using doesn't know that. But there's a bigger problem with using a RAM disk, and that's that, as I mentioned, the RAM is volatile. If you unplug it or there's any kind of interruption, all the data gets lost. Now, traditional database software, it assumes that when it writes to the disk, that the disk, that's a permanent thing. But if it writes to a RAM disk, that upends that assumption. It's not permanent. So usually this isn't a viable option. Now, as I'll show you in a moment, database software that's designed for in-memory knows that even if it's doing data manipulation in memory, it still has to make sure that that data gets permanently saved. And I'll talk a minute about how that gets done. In the in-memory database world, that's called persistence. So when you're looking at in-memory databases, if for a general purpose application, you want to find one that says it's persistent, which not all of them do. Now, in fact, there are a couple of popular databases that have an in-memory option that is essentially implemented as a RAM disk within the program itself. For example, SQLite does that. Anybody here use SQLite at all? So to create an in-memory database in SQLite, you simply use the name : memory : instead of the name of a real disk file. And SQLite says, oh, okay, that means I'm going to make this file in memory and everything happens in memory instead of on the disk. However, this is only useful for specialized applications like something that's read-only or maybe a cache, because SQLite has no way to permanently save it. It can't persist the data. Another database in that category is MySQL. It has a similar feature which they call memory storage engine. And again, it's a lot like a RAM disk, so you can create a temporary table in memory, but it can't be permanently saved. So it's probably not useful for most general applications. Usually you want your data to be saved permanently. So let's look, how do we solve this? How do we get, the speed of RAM but save the data permanently? How do vendors do that? And there's a couple strategies that they usually use in combination. So the first strategy is to periodically take a snapshot of the file and save it from memory, or save it from memory into a disk file. So this is kind of similar to the approach that Time Machine uses for backing up. Every now and then, make a copy on a set schedule, maybe once a minute or every 10 seconds, you make the copy. Of course, the potential problem with that is, what if you have a system interruption in between? Then you've got, lost whatever changes. If you're doing it once a minute and there's an interruption 30 seconds in, you lost 30 seconds of changes. And that's usually not acceptable. So to solve that, a second file is added. This is called a transaction journal. So whenever a change is made to the database, that change is immediately saved to the transaction journal file. Now, that's a disk file, but it's a very small file with a very simple sequential format. So writing to this file is really quite fast, although of course not as fast as memory access, but it's much faster than writing to a normal disk-based database, as you'll understand a little bit later. So let's put this all together to see how this works in a system to enable fast manipulation while still having permanent data. So we start with a system and we say, okay, let's open the database file, And at that time, the system will copy the file from the disk or the SSD into memory. And if the program uses the same data format on the disk and in memory, then that transfer is really fast. In fact, it's one operating system call to just load an entire file into memory. Now, we just opened the file. Nothing's been changed yet, so there's no transaction file. I don't know if you can see, it's kind of grayed out there. No transaction journal. So now we're working with the database, and the most frequent operations are usually read-only. So for example, things like searching the data, sorting it, printing reports, things like that. That all happens fully in RAM. The disk isn't needed, so you get the maximum speed. But when data is added or modified, the change, of course, is made in RAM, which is real fast, but we want to save it permanently to the transaction file. So as I mentioned, that's a small file. It's simple, so the write is relatively fast, and we don't do writings and modification as often as we do reads. And we're not updating indexes that we'll talk about later. So this is still pretty fast. Now, if on a periodic basis, then we'll do these snapshots that I mentioned earlier. So even though we're doing the transaction file, we'll also periodically save the whole database from memory to the disk. And again, if the format is the same in memory as it is on the disk, then that's an extremely fast operation. Again, just one operating system call. And when we do that, when we save the snapshot, then we clear out the transaction file. We don't need it anymore. Those are all changed permanently. So that keeps the transaction journal small and really fast. Now, if there ever does happen to be a power failure or any kind of interruption, what we do is we take the transaction journal and we update the data file, and then we've got all our data back with no loss, even though there was an interruption. So this hybrid approach is how all of the full-featured memory databases work. All the searching and data manipulation is done in RAM, and then the disk is used for permanent storage, but not manipulation. Now that we've got the basics of how data gets saved, I want to focus on what's probably the most important piece of database software, which is locating a specific piece of information. And I'm going to talk about this because this can be done differently if we're using in-memory versus on disk. And so to understand what the advantage is, I'm going to need to explain to you how it's done in disk and why there's disadvantages to that we can bypass. So let's start with the really simple approach, though. Let's say we have a database that has 15 numeric values, and we want to find where's the value 398. So in SQL, you'd specify this with a select statement like this. Find, 398. So to do that, let's see. The obvious simple approach would be to start at the top and to check each value until there's a match. So we do that like that. Just linearly search down, boom, there it is. So this technique is called a linear search. Now, the problem with a linear search is that on a slow device like a disk or SSD, it's too slow. It could take several minutes to do a linear search through even a moderately large database, even on an SSD drive if we have to scan through the whole thing. So to get around this problem, various indexing techniques were researched in the 1950s and 1960s, and a bunch of methods were devised. In 1970, a method called B-tree indexing was invented by a couple of engineers at Boeing. This diagram shows a simplified version of a B-tree index, which turned out to be the best method anybody ever came up with. In fact, this method is still being used in pretty much all disk-based databases today. Now, for the moment, I'm going to ignore how this index is created, and I just want to see how it facilitates a search. So let me search for value 398 again, and here we go through. And you can see now with this index, we're able to find that with only 4 comparisons instead of going through the whole thing. So using the simple linear search, we might have to go through the entire thing, but with the index, we can sort of jump pretty quickly to what we want. And as the database gets bigger, the speed difference between a linear search and an index gets greater and greater and greater. So this is why they're able to make disk-based databases that work in a reasonable amount of time. By the way, indexes aren't just for numeric values. A system can use an index for any kind of value, text, numbers, dates, whatever. So here's another example of an index for a database field containing text. I'm going to come back to this example, but you can see it's structured the exact same way. Now, at this point, you may be thinking that indexes are magic, and they kind of are. And that's what's allowed them, databases to do what they do for all this time. But of course, there's always a catch with any kind of magic. So far we haven't said anything about how this index got created or what happens to the index when a database value is added, deleted, or changed. So let's see what happens if we take our value 398 and let's change it, just change one character. I'm going to change it to 98. So as you can see, a whole ton of adjustments had to be made just to change this one character. Not only does the data part need to be shifted around, and my mic just fell out. Not only does the data need to be shifted, but over 1/3 of the nodes in the index had to be changed. I showed them in pink. So just that one change, all those index nodes had to be changed. If this was on a hard disk, this would be especially slow because you're going to have to wait for the head to seek around, whoop, 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 changing all those things. And even on an SSD drive, this is going to be much slower than sequential access of a single block. Now, so this has to happen every time any change is made to the database. And as the database gets larger, the tree gets more complicated, and this it gets slower and slower and slower. So if you ever wondered, like, well, why does my database get slower as it gets bigger? This is why. So there's a trade-off to indexes. The index gives us fast search speeds, but it greatly slows down database modification and adding new data. And there's another drawback, potentially, of using indexes. Notice that if you count the nodes, there's 15 data nodes in this database, and there's also 15 index nodes. So the index is taking just as much space in the file as the data is. So it's taken twice as much space as actually, just the data itself needs. This is one reason why I was able to get that huge FAA database into memory, because I didn't need all that. And what this diagram doesn't show is that indexes are usually designed with a bunch of empty padding space to help with modifications, to make that faster than they otherwise be. In fact, in some database programs, the indexes can take up to 80 to 90% of the space in the actual disk file, and the data only takes up 10 to 20%. So, kind of a reduction in efficiency. Of course, our hard drives are big, so maybe we don't care. But we do for, if we want to fit in RAM. Now, of course, most databases have more than one field. My sample here only had one field so far. Let's add another field. Now we've got a text field and a numeric field like this. Now, if we want to search both of those fields, that means each one of them has to have an index. So 2 fields, 2 indexes. That means more space, and it makes modifications slower. And as you keep adding more fields, you have to add more indexes unless you have a field that is never going to be searched. So here maybe I've added a field. I know I'm never going to search that field. So then I don't have to have an index for it, and I can save the space and performance. So most disk-based database programs let the database designer decide which field needs indexes and which don't. And you can go like, well, okay, I'm going to search this, or I'm not going to search it. Now, of course, if you have a database that isn't professionally managed, this is just another thing for the user to think about and possibly get wrong. So there are some database programs that just simply automatically index every field, but of course, there's a cost of slower modification performance and larger storage space if they do that. Now, there's another drawback, which I think is maybe the biggest drawback of the index system, which is that it restricts how you can search for data. For example, suppose I wanted to find all the names in here that have less than 3 characters. The index can't help with that because it wasn't set up, related to the length of the text. So the only way to do a search like that is to do a linear search and go back to that. In fact, my SQL code that I put up here is not allowed in standard SQL. This is really a fictional example because that's not legal SQL code. You can't do that. In fact, standard SQL only supports 9 operators. I don't know my color choice. I don't know if you can read that, but it's basically like equals, less than, greater than, except for the bottom one, which is like, which is a wildcard match. Now, that usually can only use linear searching, so in most cases, it's so slow that it can't be used except in very carefully chosen instances. Now, here's a partial list of search operators that we might like to have, but they're not available in standard SQL because they can't be made to work with B-tree indexes. Some of these could be very handy if they were actually available. And as we'll see, these operators can be available in an in-memory database that doesn't use an index. For example, maybe we'd like to have a sounds like operator that does a phonetic match, so I can find something even if I don't know the exact spelling of what I'm searching for. Or maybe I'd like to be able to use regular expressions to find something. Obviously, endless possibilities there, a lot of power, but doesn't work with an index. Or for just the ultimate flexibility, maybe I want to use a formula. So here's a formula that could locate all inventory items with a high profit margin. But there's no index for that, so we can't do that. Or here's another example, find all items that are priced below cost. Now, you actually could maybe do that in an index system, but to do that, you'd have to add another field and then build the index for that. So another field that has the calculation. So this, the downside is this takes a bunch of extra space. It requires more time. So any time a price or cost is modified, not only does the index for that field have to be changed, but also the computed field. And then, the biggest problem is you'd have to plan for that in advance. You can't just go up and say, oh, let me do this formula. You can't do that. So let's summarize, this discussion that we've just had about indexes. So on the plus side, very efficient searching with an index, but we have drawbacks of slow modification, extra storage, and limited search options. So, is indexing worth it? Well, if we go back to 1970, the RAM was minuscule. It was the only option. So, yeah, absolutely. Every database used indexing because they had to. There was no choice. But now, we've got tons of memory, and all but the largest databases can work in memory. So with that kind of speed bump, for most cases, we don't really need indexes, and we can just take advantage of the speed of the RAM and go back to linear searching and eliminate all the drawbacks. Have more flexibility, reduce storage, and faster modification. Now, by the way, I want to point out, if you really need blistering speed, you can use an index in an in-memory database and put the index in memory. For most applications, this isn't necessary, but if you're building a super high volume application, like maybe automating a major stock exchange or ticketing for a large airline, this could be definitely the way to go. In fact, super high volume applications like that is one of the fastest growing areas of in-memory database adoption. And some of the in-memory programs give you a choice whether or not you want to use indexing, so you can decide on each database, do I need it or do I not? So now you've got a flavor of the technology and how that works. I want to take you on a quick tour of what the market's like. I'm not going to go into great detail on any of these. I just want to give you a flavor of what's out there. A really common approach is to use an SQL front end and replace the disk-based database engine with an in-memory engine. So this diagram shows the typical organization. So you see we've got the SQL parser on the end, on the left, and then on the right, at interfaces with a B-tree index and a disk. So we can just take this and leave the front end in front where it's parsing SQL and doing all that stuff, and just change the back end and put in memory. So this has the advantage, it makes it easy to adapt existing applications, and you don't have to necessarily have to change your application or learn something new. You can just get a lot of the benefits by doing this on the back end. So one of the programs that does this, of course, the big kahuna in the SQL database arena is Oracle. And Oracle first got into in-memory databases in 2005. They purchased an in-memory program called times 10. And then in 2014, they actually added in-memory engine to their flagship SQL product. It's an extra cost option, but so now it's part of their mainstream main product, and they're pretty hard. I want to highlight a couple of points on this Oracle FAQ page. First of all, you notice that they're making performance claims that are very much in line with what I've been describing in this talk. And also, they're saying, well, it's really easy to move your applications because it's the same SQL front end, and you just swap in and flip a switch, and boom, you've got in-memory. Now, of course, Oracle products are really expensive, and they're really targeted for big iron applications, which probably doesn't match up with most of you here. But I still think it's important to mention them here because what they're doing is really indicative of the industry trend. And they don't have the high end of the market to themselves either. Both IBM and SAP are also strongly pushing entries in this market. And they all have lists of big Fortune 500 companies that are switching or using a lot of in-memory technology. Here's some of SAP's claims about performance gains. Another product that now includes in-memory engine is Microsoft SQL Server. That's maybe more in range. Maybe there's even some people here that are using that. Microsoft first added in-memory capability to SQL Server in 2014. Originally, it had somewhat limited capabilities, but they upgraded to much fuller features in 2016. It's also available in the premier tier of Azure Cloud Services. It's an extra cost option there for if you're doing database through Azure. To create an in-memory database, you simply add an extra custom option to the SQL custom table option. Just add that one little line, and then it'll create it as an in-memory instead of in disk. But it is fully persistent. Now, I'm not sure if Microsoft claims it's painless to convert a disk-based database to in-memory like Oracle did, but I did find this article from 2018 that seems to indicate it's not quite as simple as flipping a switch. So if any of you are thinking of doing this, you might want to look up this article because it has a bunch of tips. I mean, you can see the size of the scroll bar there. There's quite a bit of little gotchas. So in addition to some of the established players that you've all heard of that have been doing databases for decades, there's also now some new companies that are springing up specifically in the in-memory area. One of them is called VoltDB, and it's kind of notable because the creator is a guy named Michael Stonebreaker. He's the same person that invented Postgres. Probably some of you know about that. So apparently this is what he's doing now. And this is the first product that I mentioned. This actually will run on Mac OS and also runs on Linux. And they actually offer a free and open source community edition, which you can find on GitHub. So I was like, well, that's pretty cool. Until I read the fine print, and it's like, there's a pretty big catch. The community edition won't permanently save data. So if you want to save data, then you have to buy their enterprise edition, the commercial version, which is $300 to $1,000 a month. But yeah. And it's interesting because it does seem like most of the action, you'd think in memory would be at the lower end, but most of it's at the really high end of the market. VoltDB is also offered on Amazon AWS. It's $3 to $7 per hour, which works out to about $2,000 to $5,000 a month. Now, VoltDB does use SQL, but I won't go into the details, but they're a little non-standard about how they do it. So they don't really claim that you can port existing applications easily, but they do say, well, you know, if you already know SQL, you're going to get up to speed with it pretty quick. Another new memory-only database is called MemSQL. This first appeared in 2013. Doesn't run on Mac OS, but it does run on Linux, and it can be installed on AWS and Google Cloud, or you can self-host it on your own Linux servers. One of their big claims to fame is they say that it's wire compatible with MySQL. So what that means is that you can actually just take, you know, I've got a MySQL server, take it out, plug it in, and your client applications will connect to MySQL through standard MySQL protocols, as well as standard ODBC and JDBC. So if you're already running MySQL, this could be a great option because you can just, you know, dump it in and move over. For large installations, MySQL is pretty expensive also, but they appear to have a generous free tier. I saw this, there was a thing that came up about 8 months ago on a thread that they were saying that you could have up to 128 gigabytes of RAM for free. So I couldn't find that on their current website, but I couldn't, you know, I'm not sure if that's still a thing or not. But I didn't see anything that said it had been canceled. It is a closed source product if you care about that. And if you do, you might want to take a look at a program called RedisSQL. Now this is built on top of Redis, which I'm going to talk about a little bit more in a minute. That's a very popular NoSQL system. And from discussion I found on forums, it appears that this product, RedisSQL, is the work of a single developer, and it also appears that their SQL parser is a fork of SQLite. So it looks like what he did was take SQLite and Redis and combine it with some extra code. And this product looks like it's pretty affordable. The free version is fully functional. They have kind of a weird thing where if you're using the free version, it contacts their server periodically, and if that can't make the connection, it shuts down. I'm not sure what that's all about. If you get the paid version, that removes all that restriction, but otherwise the features are exactly the same. And even the paid version seems to be relatively affordable compared to a lot of these other options. Here's the GitHub page for RedisSQL. So it's fully open source. You can download the thing and compile it yourself. It's under an MIT license. It's written in the Rust language. But if you don't pay for it, you have to promise not to take out the code that does the connecting to their server. Oh, I guess you could. It's open source. Here's the GitHub page for another program called Tarantool, which is also an open source in-memory database. And this runs on Linux, FreeBSD, and Mac OS. And there's apparently a fairly large Russian company behind this product. They had a big website. It appears they have a free community edition as well as an enterprise edition, but I wasn't able to figure out if there was any difference in the features or what the price was. You know, it was one of those, call us. So, as you can see, there's quite a variety of in-memory SQL databases available. And as I was researching, I kept finding more, so I'm not sure. Maybe there's even more that I missed. And if not, there probably will be more a year from now. Now, another recent hot trend in databases, at least the last decade or so, is NoSQL databases. Now, I'm not going to go into detail about what all that is, but very quickly, instead of using tables of rows and columns like a relational database does, NoSQL databases use either key value pairs, document-based storage, graph databases, or wide column stores. So NoSQL databases are more efficient when you're working with data that's unstructured or that needs dynamic structuring. Now, like other databases, NoSQL databases all started out as disk-based, but now there are a number of in-memory NoSQL databases. And probably the most prominent is the one I mentioned earlier, Redis. I think it's the most popular, it looks like it's the most popular product in this space. It's used by a significant fraction of the web, mostly for caching, and it powers Amazon's Elasticache and Microsoft's Azure Cache services. It's open source with a BSD license, and it can run on Linux, macOS, OpenBSD, NetBSD, and FreeBSD, and it's written in C to be extremely fast. Although Redis itself is a NoSQL database, it's not SQL, it's very powerful to the point that SQL-like apps can be built on top of it with a little extra work. And in fact, as I mentioned earlier, the RedisSQL product is actually built on top of the foundation of Redis. So Redis is the engine that is actually storing the data. Some other popular software in this segment includes Apache Ignite, Memcached, Aerospike, and ArangoDB. So all of the products I've discussed so far have been designed to run on a server. None of them have an interactive user interface that's suitable for an end user. They have to be programmed in advance by a developer. Another type of database is an interactive database. Though, an interactive database can be enhanced with programming usually, they're designed to be used directly and interactively by a user. So here are some of the popular interactive databases that are available on Mac and Windows. Now, all of these are disk-based except for the last one, Panorama. As the only in-memory interactive database on the market, Panorama has some unique features like being able to search with regular expressions or an arbitrary formula, the ability to split, merge, or shift fields instantly, the ability to import or export tens of thousands of records per second, and all of these things you can have multi-level undo for any of those operations, even things like deleting a field. And that's all enabled because it's in memory and there's no indexes to modify, and so it can do operations on instances as a unit. Now, at this point, I have to disclose that, as Sean mentioned at the beginning, I'm definitely biased on the subject of Panorama since I've been the lead developer for 33 years. So I'm not going to give you the sales pitch here other than the one paragraph I just did. If you're interested in the sales pitch, go to ProView.com and press the green button, and there's a video that you can watch, and it'll definitely give you an example, a good look at what the difference is between in-memory and disk-based databases. And if you're interested, there's a free trial, and for those of you that are here in the room, I've got a coupon code, MacTech2019. It's all uppercase, no spaces, and that'll give you half off. So it's usually $100 for a year for a user. So that's good for about till next Friday. So that's basically an overview of in-memory databases. If anybody has any questions, I'm not sure how much time we still have, and I'll be around till the end of the conference too if anybody wants to grab me.